Welcome back to the fourth installment of the APEC Chemistry Chapter 8 Thermochemistry Problem Set. I am Mr. Wilkosz. Let's take a look at Problem 51. Alright, in Problem 51, you are asked to consider the conversion of C6H12O6 into C2H5OH and CO2. They want to know in this particular conversion, if the heat of formation of this solid substance is negative 1275.2 kilojoules per mole. They want to know how much heat is liberated when 750 milliliters of a solution that contains 12% of this liquid substance C2H5OH by volume underwent this reaction. So there's a lot going on in this particular problem. My first advice is to write a chemical equation for this reaction. It's not a thermochemical equation yet because we don't have delta H associated with it. That's my second piece of information, my second hint for this one. You find the delta H for the above equation by using delta H equals the sum of the delta H naught of formation of the products minus the sum of the delta H F naught of the reactants, and table 8.3. So with the chemical equation, we can turn it into a thermochemical equation if you solve through and find out that the whole reaction, the specific equation, gives off 67.2 kilojoules. And so now by adding this piece to this, we now have a thermochemical equation here. We're on our way to eventually finding out what quantity of heat is liberated when we work with this specific amount of the substance that has 12% by volume. So if you work to find the moles, you can take your 750 milliliters of solution, and for the fact that it's 12% by volume, you can figure out that there's 12 milliliters of the C2H5OH, and then you use the density and molar mass to find out how many moles of that substance is. And so you can use the chemical equation and use this last conversion factor here like a stoichiometric conversion factor, even though it has thermochemical roots. So now that we know that our 750 milliliter solution with whatever other specifications were given in the problem give us 1.54 moles of the C2H5OH, we could figure out from the thermochemical equation that 2 moles of that work to release 67.2 kilojoules. So we should get slightly less than that. We do. Negative 51.7 kilojoules are released in that particular instance. All right, let's take a look at 71. In 71, this is pretty involved. You're working with a chunk of brass, and it has certain dimensions, 22 millimeters on every side. It's heated to 95 degrees Celsius, then dunked into some water, 20 mils of water specifically, at 22 degrees Celsius. And you're asked to assume that there's no heat loss and find what the final temperature of the water is. So I kind of give a few pieces of advice on this one. Find the mass of the brass cube, so it's length times width times height gives you the volume. Once you have the volume and you know what the density of it is, you can actually find out the mass of the brass. Then I say, hey, well, let's find the heat of the brass. And so it's the heat for the brass would be the mass of the brass times the specific heat of the brass times the temperature of the brass. But you can't actually do that because you don't know what the final temperature is. That's what you're trying to find out. But don't worry, this will prove useful for us. What if we take a different approach and try to find the heat that was absorbed by the water? We know the mass of the water, we know the specific heat of the water, and oh man, same problem. Now we don't know the final temperature of this. But wait a minute. If we know that the amount of energy that was released by the brass was gained by the water, we can set what we just found up equal in an equation. So the energy lost by the brass cube was gained by the water, and we can plug in the energy lost by the brass cube and then gained by the water, and then solve through with a bunch of algebra and find that the final temperature of both those things at thermal equilibrium will be 42.1 degrees Celsius. The last problem, 83. You're asked to decide if these things are true or false concerning enthalpy. They ask if enthalpy is a state property. Yes, it is. It is path independent. They ask if the Q of a reaction at constant pressure, is it in fact true that the delta H of the whole reaction would be the delta H of the products minus delta H of the reactants? That is true. They ask if the magnitude of delta H is independent of the amount of reactants. That is not true. More stuff means more heat released or absorbed. And they ask, in an exothermic process, the enthalpy of a system remains unchanged, and that is not true. If it's an exothermic reaction, the system will release energy, therefore this is false. Energy should be released.